Have you ever wondered how your body responds to fight or flight situations? Ever thought about the chemicals at play? Today, we dive into the world of adrenergic agents, a class of drugs that play a crucial role in our body's response to stress or danger. These agents, in essence, are the conductors of our body's symphony during high-stress moments. Adrenergic agents are a fascinating group of drugs that operate by influencing the sympathetic nervous system, a part of our nervous system that prepares our body to react to threats. They work by interacting with adrenergic receptors, tiny protein structures found in various parts of the body, including the heart, lungs, and blood vessels. These agents can be broadly classified into two categories: agonists and antagonists. Agonists are like the keys that fit into the lock of these receptors. When an adrenergic agonist binds to a receptor, it triggers a series of chemical reactions that stimulate the sympathetic nervous system. This stimulation manifests as increased heart rate, dilated pupils, and a heightened state of alertness, all part of your body's fight or flight response. On the other side of the spectrum, we have adrenergic antagonists. These agents also bind to adrenergic receptors, but instead of stimulating them, they block the receptors. This prevents the binding of adrenergic agonists, thereby inhibiting the fight or flight response. The heart rate slows down, the pupils constrict, and there's a general sense of calm. To put it simply, adrenergic agonists and antagonists are like the yin and yang of our sympathetic nervous system. They work in tandem to keep our body's response to stress and danger in check, ensuring that we're always ready to face whatever life throws at us. So, adrenergic agents, in essence, are the conductors of our body's symphony during high-stress moments. Stay tuned as we delve deeper into the fascinating world of adrenergic agents in our upcoming segments. Subscribe for more because you won't find me later. Now that we know what adrenergic agents do, who are the key players? Step in, agonists and antagonists. Let's dive into the world of agonists and antagonists. These are the critical elements in the realm of adrenergic agents. They're like the yin and yang, working together in a complex dance to regulate our body's response to stress and adrenaline. Agonists are the go-getters. They're the ones that bind to adrenergic receptors and fire them up, triggering a response. Picture them as the keys that fit perfectly into the lock of our receptor cells, turning them on to unleash a wave of adrenaline-fueled reactions. Antagonists, on the other hand, are the peacekeepers. They bind to the same receptors, but instead of firing them up, they block the action. Picture them as a protective shield, blocking the lock and preventing any keys from getting in to turn on the receptor. Now, let's meet some of our key players. In the agonist corner, we have terbutaline, a bronchodilator that helps to ease the symptoms of conditions like asthma by stimulating the receptors in the lungs to open up the airways. On the antagonist side, we have atenolol, a beta blocker that helps to manage conditions like hypertension by blocking adrenaline's effects on the heart, slowing the heart rate and reducing blood pressure. Then there's methyldopa, which is a bit of an oddball. It's a prodrug that's converted into an active form in the body, which then acts as a false neurotransmitter, tricking the receptors and reducing the overall adrenergic activity in the body. Prazosin is an alpha blocker that relaxes the blood vessels, reducing blood pressure, while guanethidine works by blocking the release of noradrenaline from nerve endings, reducing the overall adrenergic activity. As you can see, these agents are not working alone. They have a team, each member with a specific task to accomplish. So how does this all come to be? Let's delve into the process of biosynthesis, release, and metabolism of noradrenaline. Noradrenaline, also known as norepinephrine, is a key player in our body's fight or flight response. But before it can spring into action, it has to be synthesized. This journey starts with an amino acid called tyrosine. Tyrosine is transformed into a molecule known as DOPA through the action of an enzyme called tyrosine hydroxylase. DOPA then becomes dopamine through the work of another enzyme, DOPA decarboxylase. Dopamine then hops into vesicles where it's converted into noradrenaline by dopamine beta hydroxylase. Now our noradrenaline is ready for release. When a nerve impulse reaches the end of a nerve cell, it triggers the release of noradrenaline from these vesicles into the synaptic cleft. Once in the cleft, noradrenaline can bind to adrenergic receptors on the next nerve cell, transmitting the signal forward. but we don't want this signal to go on indefinitely. Here's where metabolism comes in. Two main enzymes, monoamine oxidase and catechol-O-methyltransferase, break down noradrenaline, effectively stopping the signal transmission. The resulting metabolites are then excreted in the urine. This entire process is a delicate dance, with each step carefully controlled to ensure the right amount of noradrenaline is available when we need it. Too much or too little can have detrimental effects. This is where adrenergic agents come into play. Agonists can stimulate the production or release of noradrenaline, while antagonists can inhibit these processes or block the receptors noradrenaline binds to. By manipulating this pathway, we can control our body's responses to stress and treat a variety of conditions, from high blood pressure to depression. It's a complex process, but it's this precise mechanism that keeps our bodies functioning optimally during stress. Now let's get into the nitty-gritty details. What are receptor subtypes and how do their structural features impact their function? You see, receptors are like keyholes that can only be unlocked by a specific key. These keys are the adrenergic agents we've been discussing about. But just like keyholes, not all receptors are the same. They come in various subtypes, each with their unique structural features, which dictate their interaction with different agents. Let's start with alpha-1 receptors. These are mainly found in smooth muscles and glands. Structurally, they consist of a single polypeptide chain that crosses the cell membrane 7 times, creating a unique binding pocket for the adrenergic agents. This specific structure allows them to react strongly to agents like prazosin, causing constriction or dilation of blood vessels. Contrarily, alpha-2 receptors, which are mainly located in the presynaptic nerve terminals and the central nervous system, have a different structure. They also consist of a single polypeptide chain, but the arrangement of the transmembrane helices creates a different binding pocket, which makes these receptors more responsive to agents like methyldopa. Now let's look at beta receptors. Like their alpha counterparts, beta receptors also cross the cell membrane 7 times. However, their distinct structural features allow them to respond differently to adrenergic agents. For instance, beta-1 receptors, predominantly found in the heart, are highly sensitive to atenolol, which slows down heart rate. On the other hand, beta-2 receptors, mostly located in the lungs, respond well to agents like terbutaline, leading to bronchial relaxation and increased airflow. In essence, these structural differences in receptor subtypes are the reason why different adrenergic agents can cause a variety of physiological effects. It's like a well-choreographed dance, where each receptor and agent pair performs its unique routine, contributing to the overall performance. Understanding the structure of these receptors allows us to comprehend the intricate dance of chemicals happening within us. We've learned quite a bit today, haven't we? But why does all of this matter? Well, it's simple. The information we've just discussed about adrenergic agents, agonists, and antagonists, and the intricacies of noradrenaline are fundamental to our understanding of the human body's responses in health and disease. Adrenergic agents, as we've seen, play a critical role in managing conditions ranging from cardiovascular diseases to respiratory disorders. By exploring agonists like terbutaline, we've seen how they stimulate adrenergic receptors, helping to relax bronchial muscles and providing relief to asthma patients. On the other hand, we've looked at antagonists like atenolol, which inhibits the activity of these receptors, reducing the heart rate and blood pressure, crucial for patients with hypertension or heart-related disorders. Diving into the biosynthesis, release, and metabolism of noradrenaline, we've seen the intricate dance of chemical reactions that enables the body to respond to stress or danger, and also how drugs like methyldopa can manipulate this process to manage conditions like high blood pressure. By understanding receptor subtypes and their structural features, we can appreciate how different drugs interact with them. We've seen how prazosin, a selective alpha-1 antagonist, can lower blood pressure, while guanethidine works by blocking the release of noradrenaline itself. All this knowledge, complex as it may be, has a profound impact on pharmacology and medicine. It guides the development of new drugs, the refinement of existing treatments, and the discovery of novel approaches to managing diseases. It is the intricate puzzle that scientists, pharmacologists, and doctors worldwide are working to solve. A puzzle that holds the key to better, more effective, and more personalized treatments. So why does it matter? Because every piece of information, every fact, every mechanism we understand brings us one step closer to improving health outcomes, to saving lives, to making a difference. Knowledge like this is the cornerstone of advancements in medicine. So stay curious, stay informed, and subscribe for more because you won't find me later.